Welcome. So we're going to start our third module on advanced training algorithms. And we're going to start our discussion by talking about the notion of adaptivity. So let's first look at our motivation and our setup. If you recall, earlier in the course, we established a simple theorem for mini-batch SGD, which would say that the error is basically bounded by two terms. Okay? And to make sure that we get the lowest error possible, we minimize the bound with respect to the learning rate, and we find, quote-unquote, the best constant learning rate. We discussed some issues of this, and we discussed some heuristics and training techniques to mitigate those issues. Namely, there are lots of unknowns here, okay, and we also want to use sometimes a decaying schedule to make sure that both of the error terms are vanished. Okay, so here we're going to talk about the issue with not knowing certain quantities, okay, and how can we estimate them, let's say, as we are training the model. I'm going to focus the discussion on estimating the variance. So in particular, I'm going to focus on estimating sigma square here. So estimating variance, sigma square, as I'm writing here. I would say slightly more precisely, we are interested in the accumulated variance, meaning the product of t and sigma square. But these are basically the same, right? So, all right. So we want to estimate the variance, and we need some observation. What is our observation? The observation is basically the stochastic gradients we have calculated so far during our training process. So these are our G1 through GT, okay? An essential point to note here is that these stochastic gradients are not independent from each other, okay? Because to get G2, for instance, I'm looking at my current model, W2, okay? And W2 is obviously updated from W1 by looking at G1. So there is like a dependency structure here, okay? Nonetheless, we're going to ignore that for the time being to develop some intuition, okay? In particular, I'm just going to assume that these vectors are vectors that are, let's say, IID, independent, identical distributed, so potentially they have the same variance. That's what I'm saying. And in this case, because they are IID and zero mean, the variance is basically just this guy, the second moment, okay? So I'm interested to find this bound sigma square, okay? So sigma square, which is my variance, is going to be the second moment. So we can approximate, so there is an expectation here. We've seen it a few times in the course so far. So we can replace it with finite sample approximation. Essentially, I'm replacing an integral with a sum or with an average. That's what I'm doing. So therefore, this will be hopefully a good estimator of our variance, okay? And indeed, this will be a great estimator of the variance if these vectors were IID with zero mean, okay? Such that by doing some rearranging, the accumulated variance, t times sigma square, is basically the accumulation of these norm squares. Okay, so as I said, this is a great idea if we had IID vectors with zero mean, but we don't have that in practice. Nonetheless, nothing stops us to use this idea and develop an optimization algorithm, okay? And this is what we'll do. So we're going to consider our update that we have talked about before in class. So basically SGD. So you go from one solution to the next one by looking at the stochastic gradient times a learning rate. But instead of using a constant learning rate or a learning rate that is independent of G, we're going to use something that depends on G. In particular, the learning rate that we're going to use is given by this expression, where I have some constant C, which is positive, okay? That again we can determine using hyperparameter optimization, for instance, or just set it to be some small number, okay? To make sure that there is not going to be any divergence even early on in the training. And also here, kappa square is basically added in the denominator to make sure that things are numerically stable and we avoid division by 0 or division by very, very small numbers. Okay. All right, but the more important thing is that we have used this term to replace t sigma square that we had in the formula for the best constant step size. This method is called adaptive SGD. Okay, the idea is that we are adaptively estimating the variance. Okay, our learning rate adaptively changes over time as we are gathering more and more observation about the landscape of the optimization problem. Okay. Also, there is this connection to normalization method we talked about. So in terms of normalization, batch normalization, and layer normalization, we talk about activation vectors being normalized by certain variance. So here we are also doing the same thing. We are basically normalizing the stochastic gradient with variance. Okay, so that's why deep down, at least from an intuitive perspective, there is a nice connection between normalization methods and adaptive SGD. Okay. All right. So let's briefly talk about the impact of using this choice of learning rate on the analysis of the algorithm. Okay. So here is what we are doing. What the learning rate we are using. The essential change compared to what we talked about with SGD and constant step size is that this current learning rate is not deterministic anymore. It is a random quantity, right? So it is using all of these stochastic gradients. So these are random quantities. So this will also be a random quantity. And this will hugely impact our typical analysis. Let's see the implication. So let's assume that again we are working with the L-smooth function. So we said that we can basically bound the function at any point using a quadratic function, and that was our starting point in convergence analysis. Okay, so this is true for all functions that are smooth, and I'm using this update wt plus 1, which is wt minus eta t gt to update my parameter. I do the substitution, I'll arrive at this line. Now, then what we did when we were analyzing SGD was that we conditioned on wt, meaning that I'm fixing all the source of randomness that I've gathered so far, and I'm just focusing on the current source of randomness, which is the random selection of mini-batch at time t. So when I take this conditional expectation, then what we could do previously was that eta was deterministic, condition on this choice, and we could bring it out of this expectation. Here, we can't do that anymore because eta is stochastic, and indeed, even if I fix the source of randomness in wt, if I fix the previous mini-batches, I'm still using the current mini-batch when I'm forming my learning rate, because I'm also including g sub t in the denominator of my learning rate. Okay, so eta depends on gt, therefore I cannot do this. So the analysis or the usual way of analyzing our algorithms will fail. So we have to sort of find a workaround this. Okay, so to find a workaround, we're going to see what are the nice properties of our learning rate. Okay. So this is the learning rate. Again, I'm writing the expression here, which is true for all times that are larger than 1, larger or equal to 1. Now, I'm going to basically define this learning rate, which is time 0. So this is not something we use in when we in practice when we want to update our method. So this is purely for the analysis perspective. So this is C over kappa. Okay. So it's as if I'm just ignoring this term because I haven't gathered any observation yet. So what will be the zeroth learning rate? Okay. Now with this definition, then if I consider the sequence of learning rates eta 0, eta 1, etc., they actually they actually satisfy two very nice properties. First of all, the learning rate is actually causal, meaning that the learning at time t does not depend on future observation. It only depends on the current and past observation. Okay? Furthermore, our schedule is actually a non-increasing schedule, because I keep adding these non-negative terms into the denominator of my learning rate. So the denominator increases over time, so the learning rate also decreases over time, okay? But in the worst case, it's non-increasing. All right, so we're going to, as I said, leverage these two nice properties to find a workaround the issue with the randomness of learning rate, okay? So we again start with the smoothness, okay? We again substitute what our update is. So these are identical to what we talked about in the previous slide. But now we're gonna use our simple but very effective technique of adding and subtracting terms, okay? So we add and subtract basically this term that I'm writing here. I'm going to add and subtract term 1 here, okay? So which means that I'm going to arrive at this point, okay? So here now I have basically the function value at time t, this term that hopefully I know how to control using the properties of my stochastic Fourier oracle, right? So this is handling of this term is roughly, I would say, the same as before, okay? Slightly more different, but roughly similar ideas. But let's talk about these two terms, term 1 and term 2, okay? Okay. So this is the equation that we are at, and we want to see how we can use the causality and the non-increasing property of our learning rate to handle these two terms, okay? So first of all, what we can immediately observe is that term 1 is actually without any issue. We can take our expectation, and eta t minus 1 will be a constant. It can come out of the expectation. And the reason for that is causality, okay? So when I'm taking the expectation, if you recall, I'm taking the expectation with respect to the sample I'm using currently. When I fix the random selection, when I condition on the random selection of the previous mini batches. So eta t minus 1 only depends on basically the previous samples, the previous gradients. I'm going to fix them by this conditioning, so therefore eta t minus 1 will become deterministic and can come out of the expectation. Exactly like the simple SGD algorithm with constant learning rate that we studied in the beginning of the class. Right, so therefore this is great. This simple technique of adding and subtracting terms helps us to get rid of that expectation issue by leveraging the causality. Now, the second term here can also be treated easily if we assume that, let's say, the gradients are uniformly bounded. So for instance, our sample loss function is G Lipschitz, okay? So let's impose this assumption. If we impose this assumption, my claim is that this term will be bounded by the difference of the etas times G square, okay? So why? First of all, this term can be bounded by the Cauchy-Schwarz inequality with G squared, okay? But to make a claim that the whole term is bounded by this, okay, upper bounded by this, it is essential to show that this difference is always non-negative, okay? Otherwise, I would get a negative term which would serve as a lower bound, and we don't want that. We want an upper bound. And fortunately, that is actually the case, that this difference will be always non-negative, and the reason for that is the second property of our learning rate, which was non-increasing. So eta t minus 1 is always at least as large as eta t, so this difference is positive. I can, using the Lipschitz assumption and the Cauchy-Schwarz inequality, bound the second term with just this difference times G squared, okay? All right, So then I would say we are basically done, because these two terms are the terms that were relatively new compared to the typical analysis of SGD, but we can actually handle both of them. For instance, the second term can be handled quite easily by noticing that this is after taking the sum and talking about the accumulated error or the average error. This is gonna be a telescoping sum. Okay, so I can get rid of, so this will be basically exactly G squared times the 0th learning rate. That's why we defined eta 0 in the previous slide, minus eta sub t, the last one. So this term is non-negative. So this term is completely negative. I'll drop it. I'll get this upper bound. And then by definition of eta 0, I'll get a term that is completely constant with respect to the total number of iterations. So putting everything together with a bunch, I would say with a slightly more different ideas than what we discussed before when talking about the proof of SGD, we can establish the following theorem. So we're going to assume that we have a loss function, the average loss, which is L smooth. We are also going to make an assumption that the sample loss is G Lipschitz. This is something we didn't have when we talk about SGD, but it turns out that to my knowledge, for almost all of the adaptive algorithms, such as Adaptivity that we are talking about, this assumption is kind of essential. So beyond this, we make our usual assumption that we have access to a stochastic first-order oracle, returns unbiased estimators of the true gradient with certain variance, and that the samples we are using in every iteration are statistically independent. Then SGD with this step size, which we call adaptive SGD, satisfies a bond that is exactly the same as the bond with that we established for SGD in terms of the O notation. Okay, so it's exactly the same. They in the worst case converge with the same rate. The previous method, SGD with constant step size, required, let's say, using a highly optimized constant step size. Here, we are using that basically is adaptive. Okay, so it doesn't require tuning the constant as much as the previous case. So this is adaptive SGD. So in the next video, I'm going to talk about a modification to this method that bridges the gap between this, I would say, simple method, which is very nice in terms of the theoretical understanding and intuition, and the methods we end up using in practice. I'll see you there.